Okay, welcome to 7.3.2. This is the central limit theorem. Okay, so to start for this one, we need to go and get some. I'm so sorry. I don't know why I put Bryan Station High School and Bryan Station Middle School. It would have been a lot smarter to put Douglas, but I guess I can just say that I was probably tired. So we're going to go to the applet. And we're going to click on begin. Now you can see. I'm going to click on begin. Okay, so here is my parent population, right? So this is saying, all right, there were, oops, I did not mean to delete that one. Fix it, okay. So this is saying that there were like 10 people with an ACT score of whatever here is in the middle of 16. Then gradually less, working our way up over here and over here. So now we're going to take a sample of 5 ACT scores. So we had one person with an ACT score of, I don't know, 10 maybe. One person with an ACT score of 14, a 16, a 17, and a 20. Could do another. Okay, here's our next sample of 5. Now we've got 2 averages. The first one was 14. The second one was 15. We'll go again. We can go again. We can go again. So I can continue taking samples and then recording. Now here we have 2 times that we had a sample with a mean of 15. So I'm going to click the 10,000 box, and we're going to take 10,000 samples. Okay, so now we're looking at our distribution that is very clearly normal with a median of 16, and there were 1,752 samples of 5 means that had an average of 16. So that's a lot. All right, let's go back to our sheet here. Let's scroll over so that I can use all of the space. Okay. So, describe the center, shape, and variability of the distribution of ACT scores. Well, that's the population distribution, and it is approximately normal. With a population center, population mean of 16, and a standard deviation, did it tell it to us? Standard deviation of 5. Okay, then we took our, well, you can write down what you get. The blue boxes make the sampling distribution. How do we know that the sampling distribution is approximately normal? Well, we know that when the population is approximately normal, so our sampling distribution is going to be approximately normal. Also, visual analysis. Okay, so let's go back to here. It says to click clear lower 3 and then change the distribution from normal to skewed. Okay, well, I guess a mean of 8.8 on the ACT would be about right for middle school. Okay. So, what is the shape of this distribution? Well, this distribution is skewed left. And why does this make sense for Bryan Station Middle School? So that's because they are only middle schoolers. So majority score low. Oh, I guess I did have a plan when I wrote it, BMS. Okay. Now we need to change the bottom two drop-down menus to mean. The first one should be n equals 2. And the second should be n equals 25. Okay, mean, n equals 2, n equals 25. Go. Crap. Okay, mean, n equals 2, n equals 25, mean, 10,000. Go. Okay, here's our new distribution of means with a sample of 2 and our distribution of means with a sample of 25. Now we know that the bigger your sample, the smaller your variability. So here we have a much bigger sample, 25 instead of 2. So with a much bigger sample, we have a much skinnier curve. That makes sense. Okay, describe the shape of the sampling distribution when n equals 2. It is skewed right. Oh my god, did I say skewed left earlier? This is why I need you guys in class with me, because otherwise I don't think before I speak. Okay, skewed right, because I put my right hand down to squash it over there. So it is skewed right, not as much as the population. And our sampling distribution when n equals 25, this is going to be approximately normal now, not skewed. And we see that when the sample is large enough, the key is there is that it had to be large, right? We had to decrease our variability so that everybody was contained here and we weren't trailing off to the left or squashed up, trailing off to the right or squashed up on the left. We needed all of our things here condensed. Well, where is it? When our sample size is large enough, the sampling distribution will, not wish, will be approximately normal. That's our key here. That is the central limit theorem. That is our central limit theorem. And large enough is very subjective, depends on how wonky your population is, depends on how big your population, but let's say that's when n is greater than or equal to 30. That's a big enough number, it will probably not lead you wrong. So now we got to get to our big ideas. So we only have 2. First one is our central limit theorem. The sampling distribution of the sample means will be approximately normal. When the sample size is large. And we are arbitrarily saying that that's when n is greater than or equal to 30. The second one is rehashing probability. If the distribution is normal, so if the sample size is large enough, why is this tilted? We can use it to find z-scores. And then we can use those to find probability. So the z-score is going to be equal to the sample mean minus the population mean divided by the standard deviation of the sample means, which is the population standard deviation divided by the square root of the sample size. That's not new. That's just rehashing that same thing. And that is 7.3.2.